Hello, welcome back. In this video, we'll discuss the ferroelectric, piezoelectric and the pyroelectric materials and some of their applications. The ferroelectrics, pyroelectrics, piezoelectrics, essentially they are all dielectrics. So we have the ferroelectrics, pyroelectrics and piezoelectrics. They are all dielectrics. They are dielectrics with certain special qualities. These three categories of dielectrics are called as active dielectrics. The piezoelectricity is exhibited by the piezoelectric materials or piezoelectrics for short. This is a unique effect exhibited only by the piezoelectric materials. In fact, there are two different types of effects. One is the piezoelectric effect and the other one is inverse piezoelectric effect. It is the property of a material. When the material is subjected to mechanical stress, opposite electric charges are developed on opposite sides perpendicular to the direction of the applied force. That is what is called as piezoelectric effect. The property of becoming electrically polarized when mechanical stress is applied. Property of becoming electrically polarized when mechanical stress is applied is known as piezoelectric effect. And the piezoelectric effect, pyroelectric effect, similarly the ferroelectric effect, they all can be seen in crystals that do not have center of symmetry, is not present, or they are also called as non-centrosymmetric crystals. The piezoelectric effect, ferroelectric effect and the pyroelectric effect can be noticed in solid dielectrics that are crystalline in nature, and those crystals should not have center of symmetry or they are non-centrosymmetric. Only then one can notice the active dielectric properties in the dielectrics. An example for the piezoelectric materials is quartz. Quartz is nothing but silicon dioxide. So if you consider this as a quartz crystal, when the tension is applied, you notice that opposite charges are developed on opposite sides perpendicular to the direction of the force. What is the direction of force? Say if this is the direction of force, then you see positive charges are developed on the top side and the negative charges are developed on the bottom side. It is called as piezoelectric effect. Similarly, when the crystal is compressed, negative charges are developed in the top side and positive charges are developed in the bottom side, but these two charges are developed in a direction that is perpendicular to the direction of the force. The force is toward the center of the crystal. The development of charges is perpendicular to that. So you have the negative charges developed on the top side and positive charges developed on the bottom side. Since this kind of a charge development is possible, these materials can have a wide range of applications in the industry. When piezoelectric crystals are subjected to mechanical stress, tension or compression, opposite kind of charges are developed at the opposite faces perpendicular to the direction of the applied force. And the charges will be proportional to the applied force. Developed charges is proportional to applied force. There are a variety of materials that exhibit the piezoelectric effect. Examples for the piezoelectric are quartz, ceramic piezoelectrics. Certain ceramics also they exhibit this property, and certain semiconductors. Quartz in its pure form exhibits this property. The ceramics are barium titanate, lead zirconate are some of the examples. Gallium sulfide, which is a semiconductor that also exhibits piezoelectric effect. Zinc oxide and cadmium sulfide. These are some of the materials that exhibit the piezoelectric effect. Applications are: piezoelectric materials are widely used in industry, namely in non-destructive techniques. They are used in producing ultrasonics. They are used as transducers. They are also used as sensors. Ferroelectricity. The ferroelectricity can be noticed in ferroelectric materials. The ferroelectrics are a special form of dielectrics. They undergo spontaneous polarization. So they exhibit the spontaneous polarization. So these materials will have spontaneous polarization, and the polarization can be reversed by suitably applying the electric field. These materials, they exhibit a property known as hysteresis. When the external electric field is applied, one can notice the changes in polarization. When one tries to plot the external applied electric field versus the changes in polarization, we notice a loop that is similar to the hysteresis of magnetism. They are also called in the ferroelectrics as hysteresis. This is a unique property that can be noticed in ferroelectric materials. The spontaneous polarization ceases to exist in ferroelectrics at a temperature known as Curie temperature. It is denoted by a Tc. Up to this temperature Tc, the ferroelectric material will have the spontaneous polarization. Above this temperature, the spontaneous polarization ceases to exist due to the thermal disorder. This is called hysteresis loop. Loop or ඵ-claz. Along the x direction, we are plotting the applied electric field intensity. Along the y direction, we are plotting the polarization. Initially, there is a small amount of polarization. This is due to the spontaneous polarization that is already there in the ferroelectric material. When the electric field is increased from 0, the polarization increases initially quite fastly. When the electric field is further increased, the polarization increases and reaches a point beyond which the polarization doesn't change even if you increase the electric field intensity. This polarization is called as saturation polarization, which indicates that all the dipoles in the ferroelectric material are aligned in the given electric field direction. After attaining the saturation polarization, if one reduces the electric field intensity, the polarization, it doesn't follow the path that it has followed while increasing the electric field intensity. Rather, it chooses to follow a new path. Along this green line, it decreases. So slowly it decreases and it reaches a point here. One interesting point one can notice is, even when the electric field intensity is 0, you have a large polarization in the ferroelectric material. And this polarization is called as the remnant polarization. After reaching 0, if you reverse the field direction and increase in the negative direction, then you see that the polarization decreases and it reaches 0. The polarization becomes 0 for a value of the electric field intensity in the negative direction. The electric field intensity required to make the polarization 0 in the ferroelectric material is called as coercive field. The electric field intensity for which the polarization in the ferroelectric material becomes 0 is called as coercive field or coercive field strength. Now beyond that, if you increase the electric field intensity, one notices the polarization developing in the opposite direction slowly increases and reaches a saturation point. This corresponds to saturation polarization in the opposite direction. After attaining the saturation polarization, if one decreases the electric field intensity in the negative direction, then slowly polarization decreases and reaches a value for 0 electric field intensity, which is called as the remnant polarization. Beyond that, if you change the direction of the electric field intensity and increase the electric field intensity, you notice that the polarization decreases and becomes 0 for an electric field intensity represented as plus EC, for which the polarization becomes 0. This is also called as coercive field. The coercive field is represented with EC plus minus. After that, if you increase the electric field intensity, the polarization increases and reaches again saturation. Once again, if you decrease, the polarization reaches PR and EC and another PR on the negative side. So it always will be moving along the hysteresis loop. It will not come back to the initial starting position. This is what is called as a hysteresis loop. The examples for ferroelectric are quartz, lithium niobate, barium titanate, lead zirconium titanate are some of the examples. One of the major applications of ferroelectrics is they can be used to store electrical energy in capacitors of a circuit. Pyroelectricity. The pyroelectricity is exhibited by the pyroelectric materials, or for short, pyroelectrics. These materials will also have spontaneous polarization, but the spontaneous polarization undergoes small changes when the temperature of the pyroelectric is changed. The effect is called as pyroelectric effect. Is the change in spontaneous polarization when the temperature of the specimen is changed. Since the polarization is changing with respect to the temperature, one can define a quantity that is known as pyroelectric coefficient. The pyroelectric coefficient is represented with a lambda, and it is defined as dP by dt, where P is the polarization in the material, T is the temperature. So lambda is defined as the change in polarization per unit temperature change of the specimen. So lambda is equal to dP by dt. Since the temperature can cause changes in the polarization, these materials can be used as charge sensors and also as temperature sensors. They can sense temperature changes of the order of 10 power minus 6 degrees Celsius and charges of the order of 10 power minus 16 coulombs. Examples for these materials are barium titanate, lithium niobate. Applications are they can be used as charge sensors, temperature sensors. They are extensively used in thermal imaging. In this video, we have started our discussion with the active dielectrics. We have said ferroelectrics, pyroelectrics and piezoelectric materials, they are all called as active dielectrics. The piezoelectricity is noticed in materials that exhibit piezoelectric effect, which are known as piezoelectrics. Piezoelectric effect and the inverse piezoelectric effect are exhibited by the piezoelectric materials. The property of becoming electrically polarized when mechanical stress is applied is called as piezoelectric effect. These three different materials, they do not have center of symmetry, which is also called as non-centrosymmetric crystals. So these three are solid dielectrics without center of symmetry. We have seen the example of quartz crystal when subjected to tension and compression, the way the charges are developed on opposite faces perpendicular to the direction of the applied mechanical stress. When piezoelectric materials are subjected to mechanical stress, tension or compression, opposite kind of charges are developed at the opposite faces perpendicular to the direction of the applied force. The developed charges will be proportional to the applied force. We have seen the examples for piezoelectric materials, quartz, certain ceramics and semiconductors. Barium titanate, lead zirconate, gallium sulfide, zinc oxide and cadmium sulfide are the examples. We have seen the applications of the piezoelectric materials. They are used in the industry. They are used to produce ultrasonics. They are used as transducers. They can also be used as sensors. We have seen the ferroelectric effect. Ferroelectric effect is exhibited by the ferroelectrics or the ferroelectric materials. They possess the spontaneous polarization and the polarization can be reversed. Since the polarization can be reversed, when the external electric field is applied to the ferroelectric material, they exhibit the hysteresis loops. The spontaneous polarization will be present in the ferroelectric material up to a temperature known as Curie temperature, beyond which the spontaneous polarization will disappear due to the thermal disorder. We have seen the hysteresis loops and we have seen what is coercive field, remnant polarization. We have seen the examples for the ferroelectric materials, quartz, lithium niobate, barium titanate, lead zirconium titanate. We have seen the applications. They are extensively used to store electrical energy in capacitors of a circuit. We have seen pyroelectric materials. Pyroelectrical materials, they exhibit changes in the polarization when the temperature is changed. The effect is known as pyroelectric effect. Since with the temperature the polarization is changing, one can define a quantity known as pyroelectric coefficient. The pyroelectric coefficient is represented using a lambda, which is dP by dt. It is defined as the change in polarization per unit temperature change of the specimen. These materials can be used to sense temperatures of the order of 10 power minus 6 degrees Celsius, and they can also be used to sense charges of the order of 10 power minus 16 coulombs. The examples are BaTiO3 and lithium niobate. Applications are they can be used as charge sensors, temperature sensors, thermal imaging. Thank you.